here we have a molecular orbital diagram for the CO molecule. So again, it's drawn in the familiar pattern. You have here on this side, you would have the energy. So the energy is going up there. So you have the carbon 2s orbital, and you have the carbon 2p orbitals. So of course we don't include the 1s orbital. Why do you think we don't include the 1s orbital? Any idea? Sorry? They're not valence electrons, yes, so they won't be involved in the bonding. So something like the 1s orbital is core, and that will be pretty much for, say, something like CO, the 1s orbital in the CO molecule will be pretty much similar to what it is in the isolated carbon atom. Okay, so on this side, then, so you have the carbon, and here you have the oxygen orbitals. Again, you have the 2s and the oxygen atoms. And what you'll notice is, as is drawn on this slide here, the oxygen orbitals are slightly lower in energy than the carbon orbitals. And does anybody understand why that's the situation? Why have I drawn them like that? Okay, right. Well, which is the most electronegative atom? Oxygen or carbon? Sorry? Oxygen, yeah. So oxygen pulls its electrons tighter to itself because it's got a higher charge. It's further up on the periodic table, so it's got a higher charge. So it pulls its electrons closer to itself. So that means that the electrons in especially in the 2s orbital of oxygen, are lower in energy. It's a more stable situation. So stability means lower in energy. So when you're drawing a molecular orbital diagram like this, you have to draw it. It should be schematically shown lower in energy than the carbon. The same thing, not as much for the 2p, but the 2p will also be at a lower energy. The 2p electrons in oxygen will be at a lower energy than the carbon 2p electrons. So that's why they're drawn lower. And again, based on what we've done just 2 minutes ago and what you've learned previously, you should form a sigma bonding orbital and a sigma antibonding orbital from the 2s orbitals of the carbon and the oxygen. And what you'll notice here is that this is much closer. The bonding orbital is closer in energy to the oxygen. And that's what happens when you've got two different electronegative atoms combining. The bonding orbital is composed mainly of the oxygen. The oxygen is a greater contribution, whereas the antibonding will have a greater contribution from the carbon. Okay, so that's the 2s, and then you have the 2p, and you have here a complex series of lines which we're not going to go into in much detail, but basically you have the same type of bonding that we talked about for the p orbitals. You have here, we see just 2 pi orbitals of the same energy, the degenerate, and these are the side-by-side overlap of the p orbitals on the carbon and the oxygen. And you also have this one here, the sigma, and that's the pz, mainly due to the pz combination, the sigma bond formed between the p orbitals. Now what happens in this molecule CO is that this sigma is pushed up quite a bit. Usually this is down here, but in CO, for a variety of reasons, it's pushed up quite a bit. And essentially it's very close, if you like, to the energy of the oxygen atomic orbital. So when you have an orbital like that that's very close to the energy of the atomic orbitals, then usually we would call this a non-bonding orbital, or NB for non-bonding. Okay. So that's one. There's other different types. Sometimes you have no counterpart over here, and you'll get orbitals there for different molecules, not for the CO molecule. But a non-bonding orbital is usually around the energy of the isolated atoms.